Okay. Hello, we're on the home straight. Thank you for hanging on in there. Okay. So, what were we talking about last Friday? We were talking about synchrotron radiation. Now, have you had a look through the example questions and the worked examples in the notes? Again, I'm just reminding you to have a work through them and show that you can calculate each of the numbers which are given, and you'll find that will stand you in good stead. So, we were talking about synchrotron radiation, and remember our basic idea here was that of the electron, in this case, which was moving relativistically, and it was making some amount of radiation, and because it was travelling relativistically, I had the different features of that radiation. I had the fact that the radiation was confined to a size 1 over gamma. I had that the power scaled as gamma to the 4th, okay, and also the pulse length was very, very short, okay. I think I labelled that tau last time, and that goes as 1 over gamma cubed. What was it now? It was EB over m0, right, or thereabouts, okay. And it was the latter part that led to that notion that rather than having a single frequency of emission, I had multiple frequencies. It's a Fourier transform of the fact that I have a pulsed emission. That's the reason why I have that broadband spectrum. But it leads to a few interesting questions. So in this lecture, we're going to just finish off that, and we're going to talk about some other things, Bremsstrahlung and Cherenkov, and we'll look at some of the more exotic ideas around these radiation production mechanisms. Okay? Now, the first thing to remember, imagine I'm looking from the side. So from the side, my non-relativistic charge, okay, so it's executing orbits like so. Okay, zoom in a little bit because I'm writing very small today. So clearly, I'm seeing a charge oscillating left and right. Okay, and when that charge oscillates left to right, say it's an electron or a proton in the non-relativistic case, the polarization direction is along that axis. The emitted cyclotron radiation has a frequency which is equal to the cyclotron frequency, and has a polarization which is in the plane of the motion of the charge. Obviously now, if I look above that plane, so rather than looking side on, I now look from above. If I look right from the top, I'll see circular polarization, won't I? But if I look at an angle, I will see elliptical polarization. So out of the plane, if I observe out of the plane at some kind of angle, okay, let's say like so, then I will see, in general, I will see elliptically polarized radiation. Right? Now the same thing is true for synchrotron radiation. In synchrotron radiation, so this is cyclotron, exactly the same thing is true of synchrotron radiation, where of course here the only significant power emitted practically is from electrons. I'm only labelling them as electrons. Again, I have linear polarization when I'm observing in the plane of the motion. So if I go down to Oxford and I stand at the same height as the electrons in the hall of the synchrotron radiation source there, it's called diamond, okay? Then if I observe at that height, I will see linearly polarized radiation, but if I look slightly above or slightly below, it doesn't have to be a great deal above or below, I will start to see elliptically polarized light coming off. But importantly, the wavelengths are all different, okay? They're extended into a much higher wavelength, much higher energy band, proportional to gamma cubed, okay? And I have a variety of frequencies emitted. It's broadband. But there's a little piece that was missing, okay? So the first piece to wonder about is I'm going to draw that picture again of a steady current. And I'll relabel my Larmor formula. I'll rewrite my Larmor formula, because there was something I alluded to right at the beginning, which is P is equal to Q squared over 6 pi epsilon naught C cubed A squared. So we already saw that if I had a smooth distribution of charges, in other words a steady current, there's no radiation at all. So I'm going to think entirely the other way around now. I'm going to think, what about if I have two electrons nearby to each other? Okay? So I put one electron here and another electron right next to it. So really, if I thought of them radiating separately, I would write down the power as being equal to E squared over 6 pi epsilon naught c cubed. And I'd have two of them, wouldn't I? I'd have two sets, two electrons emitting. Boom. Factor 2. Okay? So this is what is known as incoherent synchrotron radiation. The power is proportional to the number of charges, and that's what we've sort of tacitly assumed all the way along. But our Larmor formula implies something different. It implies if the charges are next to each other, they should emit as if, like so. What I do is I put P, and then rather than Q, I put 2E into that equation. Okay? Right. And now it is equal to 4, so I'm going to say this is P1. That's the power from one electron. Okay, and the power from two electrons, if I just add it up naively, is twice the power of one electron. P2 equals 2P1. But if I imagine the electrons lying right on top of each other somehow, they should have a total power emitted 4P1. Okay? If they emit together. Well, if they emit together, I'm going to call that coherent synchrotron radiation. Right? And the question is, which one is right? Okay? And the answer is both. So, coherent radiation, so the complication here is that these two electrons, whether or not we regard them as being close together, is to do with the wavelength they're emitting at. And they will emit together if the wavelength they're emitting is comparable to their separation, and they will emit separately if the wavelength they're emitting is small, comparable to their separation. Okay? So closely spaced charges, if the spacing is of order L, then wavelengths of L or bigger, they will emit proportional to the charge squared. And if they are far apart compared to that compared to that emission wavelength, they emit incoherently. Okay? That's a remarkable fact. Because what's really peculiar here, there must be something going on quantum mechanically, which we won't go into, whereby they're communicating when they release one particular photon. So that Fourier transform statement that I had before, that was a statement about pulse lengths, wasn't it? Right? And somehow we said that because the pulses were short in time, I emit lots of frequencies. But we know, don't we, that these are discrete photons, and somehow they're communicating with each other when they're being emitted. So we won't worry about that. All we'll say is we can definitely say that we can draw a graph like this. So this is what the coherent radiation looks like. Okay? So this is our universal curve. Our universal curve has a critical frequency, omega c, and what I'm plotting is I'm plotting the emission frequency as a function of the, as a ratio with the critical frequency. Okay? So one is up to the right somewhere. Okay, so the half power point is somewhere about there. That's where omega c is. Okay? Right? So obviously up at this end, I've got lots of short wavelength photons. And as I drop in emitted frequency, I'm getting a larger and larger number of low energy photons, of longer and longer wavelength photons, so the wavelength is going up. And what this dotted line here is showing, it's showing me the enhancement I'm getting because of the coherent emission. So clearly, what we're saying is that at this point here, I've set the size of the emitting bunch of electrons to be about equal to that wavelength. Okay? So for example, if this is a keV or so, that'll be about an angstrom, and we're going up here something like 10 to the 6 times bigger, 10 to the 7 times bigger than that. So rather than being an angstrom, it's 10 to the 7 angstroms, which is what? Maybe a millimeter radiation. So millimeter wavelength radiation will see a coherent enhancement if the electron bunch is of the order of a millimeter in size, and so on. If it's shorter, then I will see coherent emission of that shorter bunch. Okay? So think of it this way. Here is my bunch. So if the emission wavelength is that of the size of the bunch, then the whole thing will emit coherently. But little pieces of it, okay, if that's the wavelength of emission, then this bit will emit coherently, and this bit will emit coherently. Okay? Which is why, down at this little region here, you get basically, as you approach as the emitted wavelength approaches the size of the bunch, you will start to see this coherent enhancement. Okay, all right? So this radiation here, the power is proportional to the charge on the bunch, QB, okay? Whereas here the power is proportional, I should do proportional signs, proportional to QB squared, okay? So you can see the enhancement is basically proportional to the number of particles in the bunch, of each electron bunch. And that's why this number here is of order 10 to the 10. It's absolutely vast, okay? So if I have a lump of electrons moving together and they have about 1 millimeter in size, then at 1 millimeter emission wavelengths, you get 10 to the 10 times more radiation out. It's absolutely enormous. So that's coherent radiation. All right? So that's all you need to know. That you can go into this a lot. It's a fascinating area. Now, so that's synchrotron radiation. We're now going to talk about Bremsstrahlung radiation. So remember, all of this we were talking about was to do with the motion of charges through some kind of field. So all the way through we were talking initially about how an accelerated charge generates radiation. We then stopped by and talked about the motion of charges through a magnetic field. Bremsstrahlung is the motion of charges through a strong electric field. Now remember, when we compared electric fields and magnetic fields, we found that the acceleration from a common or guarded electric field of, say, kilovolts or 100 kilovolts per meter was insufficient to provide a decent acceleration. Magnetic fields have that extra factor of C on them, so they give a much larger effective acceleration for rapidly moving charges. Okay? So in order to get anything interesting from an electric field, it needs to be a very, very strong electric field. So that strong electric field we can find in the nucleus. Okay? Now it's called Bremsstrahlung. I'm going to put on my best German accent because it comes from the two words Brem, which means breaking, and Strahlung, Strahlung, there we are, Strahlung, which means radiation. So a Strahlungsquelle, that's my terrible German accent, isn't it? But Strahlungsquelle is a radiation source. So these are all Strahlungsquelles. Okay? So breaking radiation implies that the moving charge is being slowed down by some kind of force, and this is a nuclear force. Right? So an example of this is, imagine I have some electrons, and they might have an energy from, say, 10 to 20 MeV, say, of that order, right? So gamma is of the order of a couple of hundred or so. Okay, so these are electrons. And they encounter a big thick lump of material, and a convenient lump of material that can stand a good heat load, because I'm going to be smacking electrons into it. It's a tungsten target, okay? So you can look up what the Z value is, and it's the Z that's important here. All right? Yeah, let's zoom in a bit. And what happens is, when I do that, and this has been known about since the earliest days of modern physics, is I generate X-rays. And what I find is, I generate a broad spectrum of X-rays, okay? And that broad spectrum extends, if I measure the energy of the photons emitted, the energy of the photon extends up to whatever the kinetic energy of the original electrons were. Okay, so if it's a 10 MeV electron, I might have 10 MeV photons. Okay, but I don't have many of them. Mostly I have longer wavelength photons. I have lower energy photons. Okay? And I see this effect with any material which has a high enough Z, okay, and also, of course, a large actual density, which might be 7 or 8 or something like that, maybe a little higher. And that's conveniently obtained if I have some kind of robust metal. And these are the refractory metals. Okay, we have tungsten, tantalum, rhenium, molybdenum, vanadium. Usually the first two because they're cheaper. Okay? So I wish to explain this. Well, as we alluded to, it works as so. It works like as follows. I have, as the electrons pass through the material, remember they have a reasonably large energy as they enter, and I can draw a diagram like so. Here's my electron, and it moves initially in a straight line through the solid material, and it passes nearby, it happens to pass nearby to some ion with an ion charge Q. So I ignore the electrons. Okay. I'm assuming it's the ions that are doing most of the force. And the distance of closest approach, I'm going to label B, and that is the impact factor. Okay. And because of the electrostatic force that's applied to that electron, its initial velocity is changed to some final velocity v prime due to that Coulomb force. So really I should draw it like this. It comes out, okay, at v primed. So obviously the power emitted, the electron doesn't care what the acceleration or the force is that's acting upon it. It's simply equal to q squared. Q here is the charge of the electron, and A squared, A is given by the force from that electrostatic force, and it varies with time. There's a retarded time, but it's just the same as it was before. Okay? And that's just the Coulomb force. So you can see that for a large enough impact factor, the electric field, that if V prime is approximately parallel to V, so the electric field as you pass by the ion is more or less perpendicular. Okay? But the acceleration changes. I approach, okay, the distance changes and the force changes. Okay? So I have a variable acceleration and therefore I have a variable power. Right? Okay? And because it varies, we can write down the acceleration occurs over time delta t, which is something like 2b over v. Yeah, that's the order of magnitude of the time over which the acceleration has taken place. And similarly to what we talked about before, that means that the maximum frequency of emission must be v over 2b. So it's the same as the kind of argument we had for synchrotron radiation, isn't it? Okay. And the other thing we know, of course, we know that whatever happens to that electron, it cannot be induced to emit any photons which have an energy greater than its initial energy. Okay? Because the force acting upon that electron is always at right angles. So it's just like that magnetic field. Okay? So we already know that the maximum emission energy must be equal to E. So the maximum emission frequency must be the kinetic energy of the electron divided by h. Okay? That's called the Duane-Hunt law. Right? You should remember it's called the Duane-Hunt law. So all we've got to do now is let's work out a simplified diagram. This is, again, it's in the notes, so you can just watch along. Here's my ion, charge Q. There's the electron going by, and the distance as a function of time is simply equal to root b squared plus v squared t squared, okay, because it's moving in a straight line. So I'm ignoring the fact, I'm saying that v prime is approximately the same direction as v, and it doesn't change a lot. So I'm just only looking at the softer photons, as we call them, the lower energy photons. So the acceleration A is equal to EQ now. So Q is the charge on the ion. E is the charge on the electron. 4 pi epsilon naught r squared ME. Okay. So power as a function of time, I can write that down explicitly as E to the 4th Q squared. And you have to work this through bit by bit, right? There's lots and lots of big numerical factors that appear. Okay. All right, and then there's also another factor, 1 over v squared t squared plus b squared squared. Okay, so that's the distance. Oops. That's the distance. Okay. That's the distance of the electron from the ion. Okay. So that's the power emitted as a function of time due to the varying distance of the electron from the ion. So all I have to do now to work out the total power emitted, well, I need to integrate over all possible times. So the total work done by the charge on its radiation, W, is the integral from time equals minus infinity to plus infinity. Okay? So when the charge is far away from the ion, it's emitting, it's not being accelerated much, and it's going to be emitting less power. Okay? And when I do that, it's equal to E squared, Q squared, and again, try and follow this calculation through. Okay. Hopefully I'm not missing out any factors in this. There's lots of B cubes and V squared, etc., right? But the important thing is this is a certain number in joules per electron. Okay? Now that's the power, that's the total energy emitted, right, by one electron for one value of B. So I've taken one electron and it passes by a nucleus where the minimum distance of approach is B, and that's the energy given out. Okay? Of course, in our real target that we showed, we've got lots of electrons, and they all have different values of B. And clearly, you're going to have larger values of B. Most often, the electron's going to go fairly far away from the nucleus. Okay? So here's my beam of electrons, say, and the likelihood that you're going to get a certain value of B must be proportional to 2 pi b dB. Okay, that's the probability of B must be proportional to that. Okay, now Bekafey goes through this in a little bit more detail, and so do the notes. But I can rewrite this by saying, let's imagine, I imagine calculating, because I don't really know what values of minimum B and maximum B to use are, but let's try and do that. I'm going to calculate the rate of energy loss. Okay, so what am I doing here? I have a set of electrons passing by a set of nuclei, and each electron is passing by each nucleus, okay, with a given value of B. Right? So I want to count up the number density of the ions in the material, and that's a number density per unit volume. From that I can now work out the amount of energy released per unit distance. Okay, so this is adding up that W value above per unit distance travelled, and I simply add up over a set of possible B values. So I'm not going to ask what values of minimum B and maximum B I use are, because it's going to turn out to a problem. Should be 0 to infinity, shouldn't it? Should be that, right? But I should scale the probability. So I've got whatever that W was, I should scale it according to the probability of having a certain value of B, which is 2 pi b dB. Okay? And I've got to multiply by the number of electrons I've got. Okay? So when I do that integral, because I've had a 1 over B cubed in the denominator, that's in that formula for W, you can see it up there. Okay? Right? And I've got B in the numerator. When I do that integration, I have a problem appearing. So I extract out the number of ions, the number of electrons. Okay, now I've got this e to the 4th q squared term, if I look at those terms carefully. I've got this 96 on the bottom that's appeared, because I've got 4s and other things. All right, some other constants. Okay. The important bit's this bit on the right. B max to B min. So you can see that the energy loss, well, firstly, B max can be infinity, right? It contributes nothing to that integral. What it all hinges upon is the value of B min I choose. Which I don't know. It should be 0, but if I choose 0, I have an infinite amount of energy being released. So there's a conundrum here. There's a failure in our classical calculation, okay? Because really it's a quantum process. But we kind of think, okay, it's no good to have an infinite power, right? But we do know that the total energy emitted by any given, the maximum energy emitted by any given electron when it goes by a nucleus, it can't be more than the energy it had to begin with. So that presumably is setting some value of B min, right? It can't have a B min smaller than that, right? Okay. So we could set that, right? We can also set, our whole calculation, remember, our whole calculation was based on this assumption here. Where did it go now? Here it is. Okay. Our original calculation was based on the assumption that V primed, right? V primed was roughly parallel to V, so our calculation was also a bit deficient there. So it turns out what we can do, and this is not this is meant to illustrate how to get around this problem. Okay, what we can do is we can say, let's calculate what the size change in delta V is, and say that the limit of validity on our calculation that we've done above, that's that one there, okay, is to do with it's only valid when delta V is much smaller than V, the initial velocity. Okay, right? So we want to calculate when delta V is of the order of V, and then this calculation is invalid. Okay. And that allows us to set a value of B min. It's not very satisfactory, but it gives us a rough idea how to do things. So we calculate delta V as follows. Delta V we can calculate explicitly by simply integrating the force as a function of time over all times. Okay? And that's what I'm doing here. So all I'm doing is I'm calculating the total change in velocity. I'm applying the acceleration, and when I calculate that, I find it's equal to 2qE over mBv. So whatever the value of B is for my, so whatever, you know, I point the electron, and as it passes by that particular nucleus charge Q, and it goes by with the closest distance approach B, then delta V, as B reduces, delta V becomes closer and closer to V, right? So we could say that our minimum valid value of B is equal to 4qE over pi mV. Okay? Right? That's one way to do it. And you can see that's not far away from another limit, which is when B is of the order of h bar over mv. Okay? That's a restatement of de Broglie's relation, isn't it? That we must start taking quantum effects into account when the momentum of the object passing by is equivalent to a size b. Right? So this formula up here is still fine, right? As long as I stick in a decent value of b min, but I reflect upon it and say it's got a limitation, and that limitation is because of this quantum effect. Okay? So I can use a b min, and what we do is we put a thing called a Gaunt factor in that accounts for that ratio of those changes. I should do a quantum calculation. Here we've done a classical calculation. This is a classical course, but it allows us to calculate some very important things. It says to us, I can get a rough idea what the power emission from Bremsstrahlung is as a function of the various features of the system. The number density of the ions, the number of electrons that are going by, the charge on the ions, so that's the nuclear charge, okay, and some other factors. And as long as I put in a reasonable B min value, I can get a rough idea how much power I'm going to get out. Okay, and the Gaunt factor, as it's called, allows me to put a numerical correction so I can relate this theoretical calculation to the practical one. Okay, so it's not entirely satisfactory, but it's not bad. So let's try and calculate that. Let's try and calculate it for a very important case, which is called free emission. Okay, so I have a plasma, right? And the plasma is composed of ions and electrons again. And because the mass of an electron is clearly obviously much less than the mass of an ion, and we know that the power emitted is proportional to a squared, what it tells us is that when I have a system of ions and electrons moving around, the ions don't see much of an acceleration and they don't radiate much, whereas the electrons do see an acceleration and they do radiate a lot. So if I have a plasma, the electrons radiate, okay, and the ions don't. And it's called free emission because both the ions and the electrons are moving. And let's calculate that. The Bremsstrahlung power, okay, is about equal to NE/Ni, that's an e to the fourth term, q squared. So you can see if I change the plasma, if I change from hydrogen to helium, for example, I'll change q and I'll change the power. Okay. There's a lot of factors that appear there, but that's the power in watts per meter cubed. Okay. And if I carefully work that number out, it's something like 1.85 times 10 to the minus 38 times the number density of the electrons, the number density of the ions, which of course may well be equal in most plasmas, and that's in watts per meter cubed. And I've got this number is true when I give the electron energy. You see here the power goes as v squared, so it's proportional to the energy of the moving objects, here the electrons. And this EK here is the kinetic energy of the electrons. Okay, so that's a numerical version of the expression above. Okay. So there's an example question sheet that you should work through, and you can see the most important thing here is that the Bremsstrahlung power is proportional to the ion charge squared. Okay. All right. So that's Bremsstrahlung. So one of the most important examples of that, imagine I have a fusion reactor and I have some kind of plasma, for example a jet. The plasma volume might be something like 100 meters squared. If you put in the ion density and the electron density, assuming they're the same, you can work out what is the amount of Bremsstrahlung power emitted, and because the plasma has a certain finite temperature, it will radiate because of the electron acceleration by the ions, and if you put heat into the plasma, it will cool itself down. Okay, so plasmas are cooled by Bremsstrahlung. And that places an upper limit, Bremsstrahlung, Bremsstrahlung, 2 S's, 1 H, and 1 M. Okay? So plasmas are cooled by Bremsstrahlung, right? As you try to increase the temperature and increase the plasma density, they will cool faster, and you need to pump more heat in just to keep it at a steady temperature, right? Even before you try to squeeze it to make it actually do anything useful, which is one of the reasons why fusion power is very, very hard. Okay. Okay. So that's Bremsstrahlung. So we've been through two situations where we have the action of fields upon charges. We had the action of magnetic fields upon moving charges, and there were two interesting cases. One of them was cyclotron radiation, and the other was synchrotron radiation. The difference was whether one was relativistic or not. Synchrotron radiation is from relativistic charges, cyclotron radiation from non-relativistic charges. We could work out some pretty specific formulae for the amount of power being emitted. With Bremsstrahlung radiation, our classical calculation is more complicated because of the impact factor. But fundamentally it's the same kind of thing. The difference here is we have a varying acceleration as a function of time due to that varying distance of the electron as it passes by the ion. And only ions are doing this acceleration because it's the only thing that can provide a strong enough electric field that can give us a reasonable acceleration, therefore a reasonable power emission. Right? Now, all the way along, we had this basic idea of radiation being caused by acceleration. Right? And that's generally speaking true. But there is a particular situation where it isn't, and this is Cherenkov radiation. So we should look at that. Okay. So all the way through we were saying that the Larmor formula arises because we require acceleration in order to give rise to radiation. And our statement about that was that the accelerating charge gives rise to a fluctuation in the wavefronts, fluctuation in the field lines, such that there is a wavefront being emitted that travels away from the charge. Okay? And when a charge is moving in a vacuum, that can only arise if the charge itself is being accelerated. Okay? However, you can have a uniformly moving charge. So Cherenkov radiation is an example of a uniformly moving charge, one moving at a constant velocity, that does radiate. Now we already saw that that does not happen in a vacuum. Okay? But it can happen if the velocity of the charge is larger than the phase velocity of the material through which it is travelling. How do we explain this? Let's draw the path of a charge. Okay. So at any particular instant, let's say the charge is there at this instant, okay. And we'll call it an electron for argument's sake, but it can be any charge, but let's say it's an electron. And the charge moves at different points of time, at any given instant, at different times, it's moving in steps, say. As it passes through this material, we'll assume the material has some response to the electric field being generated by the charge. So we can think of it a little bit like Huygens principle, can't we? When the charge is at this position, then the electric field lines that it will start to generate at that point will start to emanate away, and I can draw at a particular time later. Well, obviously this is propagating at the velocity with which the material can respond to that electric field. That's the phase velocity. So if it's a dielectric, this little wavefront is emanating away at Vp. Okay? So at each step in time, the electron will move from here to here, and in that same step of time, this wavefront will expand by a distance which is smaller than the distance the charge has travelled. That's what we mean by where we say that the velocity of the charge is bigger than the velocity of light in the medium. Okay, so this is a time step dt, and the charge has moved this far, and it's outrun the field that it has generated. Okay, so let's draw a few more though. So each time step, now this charge has moved over here, so I've got another wavefront that's appeared. Okay, or a changing electric field, and so on. But what's more interesting, if we start drawing the other ones, after 2 time steps I should draw this one here, okay, and after 3 time steps I should draw this electric field from where the charge was over there. It's gone out to three distances. This one's got to 2 distances. Okay, starting to get quite busy, isn't it, right? And this one's got to, let me see, that's 2, that's 1, and then we have here. Okay, right, so I'll just draw that one in a solid line, and this is where the charge is now, and this is where it's going to be a bit later. Now, because the charge has outrun its generation of field, there's actually a singularity. There's a shock wave, you see. I can draw a tangent to all those particular things. It's, like I said, it's a bit like Huygens principle. And that shock wave, ahead of the shock wave, there's no field at all. Behind the shock wave, there is this emanating wavefront. So I imagine filling in all the little gaps. There must be a little wavefront. So behind there's no field. Sorry, ahead of the charge is no field. Behind the charge there is a field. So there's a shock wave, and that shock wave clearly looks like a wavefront, doesn't it? And that is moving at Vp. Okay? And you can see by this geometric construction, it has some angle theta, which we're going to work out. And all of this only works because the charge is moving faster than Vp. That's how I form the shock wave. It's just like a sonic boom, isn't it? It's exactly the same, right? Now, there is some argument that this could arise in a vacuum if somehow the speed of light in a vacuum was lower than the speed that a charge could go at. Okay? But that isn't true, is it? We know that's not true. So this can only happen in real materials. Okay? It can only happen in materials which have a refractive index which is large enough such that the velocity of the charge itself is bigger than the velocity of the light. Okay? So the required speed, C, must be somewhere between C over n, so V must be bigger than C over n, where n is a refractive index, and obviously it must also be less than C, the speed of light, because the charges can't go faster than light, obviously. Okay? So let's put an example in and figure out what these are. Let's say water, and we're going to think about visible light. Water has a refractive index of about 1.3, and therefore the required velocity, C over n, we must be exceeding C over n, that's about 0.75 c. This doesn't look too bad, right? There are plenty of fast-moving charges which can go that fast. Okay? Let's work out what gamma is for that. Well, the relativistic gamma for that value of beta, this is beta, isn't it, right? So beta must be equal to 0.75, right? So the gamma for that, the relativistic gamma that goes with that, must be greater. And if I write it out in terms of the refractive index, it's 1 minus 1 over n squared, okay, which is about 1.5, okay, which is quite easy to achieve. Let's imagine it's an electron. The electron, if an electron is to create Cherenkov radiation, again, this is for emission in for visible light. So it all depends on what the refractive index is. So the refractive index changes as a function of wavelength. The required velocity will change. But for visible light, the electron must be moving, right, with a kinetic energy greater than 260 keV, okay? Which is not that much. We can get Cherenkov radiation quite easily. And remember, Cherenkov radiation does not care what the charge is. Right? It only cares what the velocity of the charge is compared to the velocity of light in the medium. You get Cherenkov radiation from anything. Right? So what is theta? Well, let's look back at our triangle. And let's imagine that time step. So this direction here is the direction of the charge. Okay, and our wavefront, okay, is being emitted at some angle theta. Okay, so remember this direction here, that's the direction in which the radiation is moving. So the wavefront, which is this other line, must be clearly at right angles to that wavefront. Okay, so that's our emitted wavefront. And I imagine what's happening over that time step delta t. Well, the charge is moving with v delta t, which is equal to beta c delta t. That's easy enough. Okay, and the wavefront has moved, okay, by whatever the phase velocity is at that wavelength times delta t, which is equal to c over n delta t. Again, pretty simple. Okay. So I'm trying to work out what cos theta is, right? So cos theta, which is the angle at which that shock wave is being emitted as the charge goes by, is simply equal to c over n delta t over v delta t. Of course, the delta t's cancel because that was just an arbitrary time step. Equal to c over beta c n equals 1 over beta n. So you can see again how the velocity of the charge required to give a shock wave depends on the refractive index n. Okay? So let's assume one end of the scale, right? So we'll assume some high energy charge. Okay, so assume a high energy particle. What do we mean by high energy particle? We say beta equals 1. Okay? In that case, the emitted angle cos theta is about 1 over n, and because n is 1.33, that's 43 degrees. Okay? So visible Cherenkov light emitted by rapidly moving charges near the velocity of light comes out at about 43 degrees. So if I had a beam of those particles passing through the material, I would have to look at some angle of 43 degrees, but I could look anywhere around that cone. Okay, that's what this looks like, right? So I see a cone of light being emitted. And the angle of that cone varies as a function of the velocity beta. So there's beta, so that's 43 degrees. Okay, a beta equals 1. And as beta falls, the angle drops down to 0. Okay? Okay, so that's the angle. So when the charge is travelling just slightly above the required velocity to emit Cherenkov radiation, you get a very narrow spot and a very narrow cone of light, and just below that you get nothing at all. Okay. Now, this is one of the reasons why, if you look inside a nuclear reactor, and there's not many that you get to look inside these days, right? But there are things called pool-type nuclear reactors, and they're interesting because they're mostly cooled with water, so you can see through them. And we said water's got a refractive index of 1.3. Okay, and the radioactive materials, after you've turned off the reactor and you've got no more fission going on, you still have a lot of beta decay of the stuff that's left behind. And the interesting thing about beta particles is they have energies up to about an MeV. Okay, so the number of beta particles you get varies as a function of the beta particle energy, so it goes up to maybe 1 MeV. Okay, that's the energy of the beta particle. And the important thing here is if your threshold is at about 0.2 MeV or so, as it is for Cherenkov radiation, you've got a whole host of beta particles that have sufficient energy to generate Cherenkov radiation. They're all going different directions. Okay, and therefore the reactor water glows blue wherever the beta particles are. Okay. So that's why Cherenkov is often thought to be blue. Now the interesting thing really here is, why does it glow blue and not white? Because all the stuff we said here doesn't care. You know, we're just saying I'm getting photons emitted. Right? Now, there is a more involved calculation, and it's called the Frank-Tamm formula, after two Russian scientists, Frank and Tamm. They got a Nobel Prize for working this out. Okay? Even though Pavel Cherenkov was the person who first noticed that this process might occur. And what they found is the following. If you calculate so what we calculated was whether or not photons were being emitted due to this shock wave, but we didn't say how many. There must be a rate of photon production. So we write down the rate of energy loss by the charge to that radiation field as a function of distance travelled and as a function of the frequency of the photons being emitted. And it turns out, according to the Frank-Tamm formula, that it's proportional to the frequency, okay? And some other factors, like so. Okay, that's the Frank-Tamm formula. Ilya Franken, can't remember his name, can't remember the other one's name. Anyway, Frank-Tamm formula. Okay, so this does explain why we have more intense emission at shorter wavelengths. So it's that fact that explains why it's blue, because we get more blue photons than red photons. So that's straightforward. So that's what they found. But there is a problem. As the frequency goes up, the energy of the photons goes up and the power goes up. And this formula predicts it's completely unbounded, right? So according to this formula, for any given small distance dx, if I integrate over all emission frequencies, there should be an infinite amount of energy released. Okay? Which is a bit troubling. Shouldn't happen, should it? Right? Any idea why this isn't actually a problem? Anyone spot that? Looking blank, a little blank. Well, if the refractive index remained significantly above 1 for all wavelengths, then you would have an infinite amount of power being emitted. Fortunately, the refractive index of materials does not behave that way. Otherwise, okay? So what really happens is the following. Let's see if we can draw a careful picture. So we saw this a couple of sections ago. I'm going to write this down in terms of the permittivity of the material, root n, but the two diagrams look the same. But I'm drawing it this way to remind you of what we drew before. And we remember that we had, as a function of wavelength, or as a function of frequency here, we had a variation in the permittivity, or equivalent to the refractive index, as a function of frequency. And remember, there were three interesting points. At low frequency, the refractive index was near 1, and near one of these anomalous regions, the refractive index rose, okay, and then it dropped back down again, and it went through this anomalous region, and then it came back up to 1. And remember, we said it had to go to 1 at very, very high frequencies. Okay. So in water, this is up here in the X-ray part of the spectrum, okay, and this is what you might call the optical spectrum down here, okay, because of course this is related to those transitions that we talked about previously. And importantly, in water, this region here, where the refractive index is significantly above 1, that's our visible part of the spectrum there, okay. And the condition where we get Cherenkov radiation is when the velocity of the particle is bigger than that refractive index. So our condition here is that it's 1 over beta squared, right? So whenever the refractive index is bigger than 1 over beta squared, or here, sorry, this is here the permittivity, sorry, then I'm getting emission in this part here. Okay, that's why I've drawn it like that. Okay? So I only get Cherenkov radiation in that region because that is when I satisfy the Cherenkov condition. And that's what solves the whole problem. That solves the infinite power problem. Okay? So I either get emission or I don't because of the refractive index, but if I am emitting it, the power scales according to this Frank-Tamm formula. Okay. So that's it. So the things you need to remember about Cherenkov radiation is how to obtain the Cherenkov formula, okay? And the important fact is that you need to have a angle cos theta equal 1 over beta n. That's the important fact to remember. Okay. So again, work through the examples to familiarise yourself with that. Okay, I think we're still on track. We've got one more lecture, so we'll come back on Friday and talk about waveguides. Okay. So if you just remind yourself about section 5, and we'll try to bring it all together. Okay, and we'll see you on Friday, and then it'll all be done. Hey, hi.
I think I missed it quickly here. This graph here, is that what was it on the x-axis?
That's the energy of the beta particle. So I have got that here to show you where you can find it in the notes. There it is. Okay. There we are. A typical beta particle spectrum is continuous from 0 up to some maximum energy. Okay. And you can see that when you have energies above 260 kV for visible light in water, that's when you get the Cherenkov radiation being emitted. Okay.
Okay. Fab. Thank you. The big formulas, like I haven't got any on my piece of paper. Are those the kind of things that do we need to like?
You won't need to know the Frank-Tamm formula.
Okay.
Okay. Yeah, you won't need to. The important thing is that the Frank-Tamm formula it's proportional to omega.
Okay.
Okay. Okay.
Thank you.
Hi. That's okay. Hi. Sure.
From lecture 10.
Oh wow, lecture 10. Wow, that was a while ago.
Yeah, I was trying to find this formula.
Yes.
Because once I got alpha,
Yes.
then
I don't have my notes on me.
yeah.
Tell you what, can you come along on Friday to the nuclear lab, and then I can go and get my notes and I can go through it line by line. So I won't be able to just recall how you do it. Go through it on the notes. Yeah, Friday in the second floor nuclear lab. Do you know where that is? Yeah, the nuclear lab side. Yeah. So I'm there all day. Let me check my diary. I'll tell you when I'm not around. Because I have interviews. Of course, I'm doing a lecture as well. So, so Friday. I'm free in the morning. Just come along sometime in the morning, yeah? And I'm also free in the afternoon as well, but obviously not when I'm giving the lecture. Okay, cheers. Did that help okay? Is that all right? I mean, the interesting question is, of course, why do beta particles come out of nuclei with different energies? Why do they do that? If you've got a certain amount of energy in decay, why do beta particles come out with different energies? Because gamma rays come out of nuclei with one energy, don't they? Right? So you've got a certain energy in the reaction, they come out with one energy. Why do beta particles? It's a similar kind of process, right? You have a certain decay. A certain amount of energy is made and it's given to the outgoing particles, and yet somehow the beta particle comes out different energies each time. What is that? Yeah. So a nucleus emits a beta particle. Could be. You know what? That modifies it. If it's a positron versus an electron, you do get slight variations on that. But there's more important effect. You know, really. What's happening in a beta decay that isn't happening in a gamma decay? How many things are coming out of the nucleus in a gamma decay? In a gamma decay, one thing comes out, just a photon. In a beta decay, what's coming out?